Look at it here. I have compiled subtopics from each chapter in Form 5, right? Okay. So we will go through this. Some of these are notes, some of these are the selected subtopics that I feel important. So as we go through, you revise with me together. Anything you don't know, you stop me. And whichever subtopics that I feel important, we just stress on it a bit more. Okay. All right. Formulas of chapter wave, very common one. Speed equals to frequency times lambda. You should know that formula. And then B is for refraction. Whenever refraction occur, this is speed in the deeper medium, lambda in the deeper medium, equals to speed in the shallow medium and lambda in the shallow medium. So these are the formulas that you have to know. And then changes in the wavelength and velocity of water wave. All right. Okay. So whenever there is a refraction of water wave, say shallow water, deep water. So shallow water frequency remain the same. Deep water also frequency remain the same. So always remember, guys, frequency will be the same. Frequency will be the same for both. Frequency remain the what I did. Frequency remain the same for both shallow and deeper water. All right. Shallow water velocity decreases, deeper water increases. All right. Wavelength. All right. For shallow water decreases, deep water increases. So basically, as the wave or water wave move from shallow to deeper, speed and wavelength increases. What remain the same? Frequency remain the same. Okay, done with this. Next, we look at another common formula of interference, lambda equals to AX per D. Then there's another formula. This is to determine depth of ocean or distance in a cave or distance from a wall as you produce sound wave, right? So always when you use this formula, take the speed of the wave given times half of the time given. The time might be given from the time you emit the wave until you can hear back the wave. So take half of it, right? So C is the formula of interference, D is to find or determine depth or distance, right? Okay. Next common questions that students might forget by now. What are wave fronts? Wave fronts are lines or surfaces joining all the crests or points vibrating at the same phase and of equal distance from the source of the waves. So you also can tell that wave fronts are imaginary lines on the surface of the wave. Wave fronts are imaginary lines on the surface of a wave. And these imaginary lines, all right, okay, on the surface of the wave, the particles along that line must vibrate in phase, must vibrate in phase. So wave fronts are maybe a path line of all the crests, maybe a path line of all the trough. That's how we look at wave front, okay? Then we have two more common explanation, internal damping, external damping. Internal damping, loss of energy to overcome forces of attraction between the particles. What is internal damping? Loss of energy to overcome forces of attraction between the particles, because there's a forces of compression and their stretching between the particles, right? So that's how we look at it. Then external damping to overcome air resistance. So damping, you have to know the definitions. Okay, then the normal things, diffraction of water, movement of water away after an obstacle or passing through gaps, all right? Then normally this is a normal question. At the bay, depth of water is shallow, water is spread to a wider area, amplitude decreases. That's the region and the reason why energy of the wave is spread and decreasing. There's a common question that asks you, why as the wave enter a bay area, the energy decreases, or what happened to a wave as the wave enter a bay area? First, you must understand a bay area is a wider area. The waves are spread to a wider area. Amplitude of the wave decreases. Energy of the wave spread decreases. So it's a more calm wave compared to the deeper area, right? So diffraction, quite important. Go through interference, very, very important. Please go through everything about interference. Okay, so might be very interesting this year when you talk about interference, because I was doing some studies last night also. So you see here, guys, listen to me. Interference questions, 2016 was question 6, section A. After that, 2019 was question 2, section A. All right. Then nothing came out about interference. Nothing came out of interference. Essays in section B of section C. Tada. Tak ada. Right. So might be very interesting. Interference part. Okay. Next. So go through what is principle of superposition interference. Two waves acquire the same place at the same time and make a langgar kan. So superposition lah. They acquire the same place at the same time, right? So we have constructive and destructive interference. Make sure you know how to identify the constructive and the destructive interference. Okay, look at here now carefully. I'm using example of sound wave. Okay, so when you look at it here, this line indicate all the crests. This line indicate all the crests. Okay, this line indicate all the crests. Goes through here, indicate all the crests. This is the crest. Okay, if you notice, this crest experience a collision with this crest. So this green dot here is confirm a constructive interference point. Same goes to here, constructive interference point. Another constructive interference point, because it's a collision between a crest and a crest. So constructive, 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 constructive. Then think of this pula sekarang. See here. If this is a crest and this is another crest, all right? So crest and crest, so in between you have the trough. The trough is here in between. So if you look at it here carefully, what they are trying to show us is that, see here carefully here, all right? A crest and a trough langgar. So this is a point of destructive interference here also. Destructive interference. See here also destructive. So the blue color cross all are destructive interference. The green color dots are constructive interference. All right. So if you use loudspeakers, the green color dots are the loud sound, constructive. The blue color cross is the soft sound because of destructive. So this is how we look at them. This is how we identify the interference. Okay. Make sure you know the differences between the constructive interference point and the destructive interference point. I'm using example of sound wave now. Sound wave. Okay. So the formula is always the same. Lambda equals to AX per D. So in SPM, it can be sound wave interference, water wave interference, light wave interference, Young's double slit. So I think you have to concentrate all the interference questions. Okay, type of electromagnetic waves. I think this one most of you are very good at this, so I'm not worried. I'm not really worried about this part. So go through all the examples. Look at this. The three common properties of all the electromagnetic waves. Number one, all electromagnetic waves are transverse, as you all know. They can pass through vacuum, we all know, and they have the same speed in vacuum. The speed of light. All of them will have the same speed. They'll have the speed of light, all right? Which will be 3 times 10 to the power of 8 meter per second. The same thing lah. Okay, next. Harmful effects of excessive exposure to EM, electromagnetic waves. Also, please go through. So, radio wave, harm body cells, migraine, headache, microwave, internal heating of body tissues, infrared skin burn, X-ray cell mutation or kill the cells, gamma ray, mutation cancer, ultraviolet, skin cancer. So all this, please go through again. All right. Okay, let's try a few questions here. Okay, question 5. Figure 1 below shows, right, the electromagnetic spectrums. So what are the names given to the waves in section W and Q? So I always call GXU. So W is X-ray, GXU, Q must be visible light. So W is X-ray, Q must be visible light. From gamma ray to the radio wave, gamma to the radio wave. Along the spectrum, which property of the radiation has a decreasing value? Frequency. From gamma to radio wave, frequency decreases. And which property has an increasing value? Sure, the wavelength. Wavelength, right? State 3 common properties of all the electromagnetic waves. The answer is here. All the 3 properties of all the electromagnetic waves. The answer is here. Transverse, can move through vacuum and have the same speed in vacuum. Okay, next, using the information in figure 1. All right, determine the type of electromagnetic wave which is used and why it is chosen. So to detect cancer and to treat cancer patient, gamma ray, higher penetrating power. To broadcast radio and television program, radio wave can, longer wavelength, better diffraction. To cook, microwave, higher heat produced. Okay, look at this one. An aerial transmits microwaves on a frequency of 2 gigahertz. If the speed of the microwave in the air is given, calculate the wavelength of the wave and how long does it take to travel? 90 kilometer. Okay, let's try, all of us. Let's try. So an aerial transmits a frequency of 2 gigahertz. The speed of the microwave in air is given. Calculate the wavelength. Okay. So wavelength, speed equals to frequency times lambda. So lambda should be the speed given, 3 times 10 to the power of 8 meter per second over giga, 2 times 10 to the power of 9. Giga 9, right, guys? Correct, right? Hertz is per second. 9. So what's the answer?
0.5, 15. 0.15.
0.15 meter. Okay. And how long does it take to travel 90 kilometer? Use another formula. Speed equals to distance per time. How long, right? Does it take? So time should be distance 90 kilometer, change to meter. All right. Divide by speed will be 3 times 10 to the power of 8 meter per second. So what's the answer, guys? Negative berapa?
4 or 5? 4.
4 seconds. So this is the time taken for the wave to travel 90 kilometer distance. All right. So interference look like very important. Basic calculations look like very important. Okay. Next. Explain forced oscillation and resonance. All right. So we go back to the idea of resonance first. Resonance is a property that occur when an object vibrates at a frequency equivalent to the natural frequency. So your object is vibrating like a glass is vibrating, and the glass object vibrate at a frequency equal to the particle's vibration frequency, which is called natural frequency. And now the question is, why your object is vibrating? because of forced oscillation due to the energy created by sound wave. So as a sound wave travel, it starts to knock the glass surface or any object. So as the sound wave hit a surface, the object started to vibrate. As the object vibrates, when the frequency of vibration of the object is equivalent to the frequency of vibration of the particles inside, resonance occurs. And the impact of resonance is that the amplitude will increase. So when the amplitude increases, sometimes these objects were displaced a further distance where they can't come back. So the whole glass will shatter or break. So resonance occurs due to forced oscillations, and resonance occurs when the frequency of objects vibration is equal to the natural frequency. Done. Okay, next. So look at resonance, please. Diagram of light waves produced through a double slit. So we have double slit and single slit. So you have to go through the differences of light rays produced by a double slit and a single slit. Okay, let me explain now. See, if you have, let's say, a light box here, and then you have, okay, a single slit here. Okay, this is a single slit. So your light ray is actually moving through from the light box to the single slit. All right. This is the light box. So from the light box, the light ray moving through the single slit. So this is the single slit. Okay. Now, what will be the observation on the screen now? This is our screen. So on the screen now, our observation will be, if you look at it carefully, right? In the center, you will get the bright line in the center, all right? And then at the side here, all right, you get another bright line, but this time it's getting smaller, smaller. On the right also, you get another bright line, which is smaller. So in between them, it's the darker line. In between them is the darker one. This is the darker one, right? This is the darker region in between them. In between them, it's a darker region, right? So, and after this also, you realize that the brighter one is actually getting smaller. It's getting smaller, all right? The brighter regions are getting smaller. So as they are getting smaller, we realize that the darker regions are getting bigger, all right? The darker regions are getting bigger. This is the darker region. They are getting bigger, all right? So when you have a single slit, try to understand, all right? In the center, you get a brighter region. Single slit, in the center, you get a brighter region. That's in the center. Okay, only in the center, you get a brighter region. And then away from the center, to the left and right, the brighter regions here, you get to know that their size is decreasing. Their size is decreasing, all right? The darker regions are, all these are darker regions, all right? So you must know that if you are using a single slit, only in the center, you get the brightest region. Then away from it, the size of the bright bands are getting smaller and smaller. It's not equal size. It's not equal size, getting smaller and smaller, all right? This is how single slit. And single slit only produce diffraction. Single slit only produce what? Diffraction of light. Only diffraction of light. Now we look at interference. So when you look at interference, all right, first as usual, you have your light box, all right? Then you have your double slit now. Now there's a double slit, two slits now. And these double slits must be very close to each other, all right? Very close. This is the double slit. So now we are using a double slit. Double slit. So what will happen on the screen now? Now on the screen, when you see the screen here, we will realize that as usual, the light ray will go through. The light ray will go through the double slit. The light ray will go through the double slit. Okay. Then on the screen here, we realize now, right? We will get equal sizes of bands of light ray. All are equal sizes. This is a perfect interference, right? So you'll get the bright line and the dark line. All are almost equal sizes only. So why are we getting this? Because this is the system that shows that we get the dark line and the bright line, okay? So we get this. This is the dark band. This is the dark band, all right? This is the dark band. So we get it equal sizes. So this is a perfect interference pattern. A perfect interference pattern. So if they ask you what is the effect through a double slit, then you can tell through a double slit, the effect is, if it's through a double slit, the effect is interference and diffraction. So double slit, interference and diffraction. So you must know the differences of the size they formed and the observations. Okay, next thing to the other things that we have to look at here. When you have interference, all right, the formula was lambda equals to AX per D. So when you increase the A, so what is the effect? See, lambda per A is equals to X per D. So when you increase the distance of A, so X distance will decrease. That is the most important thing we are looking at. X distances decreases. X is the distance between two consecutive points of constructive or destructive interference. It's decreasing. Then look at D. Look at the formula. Lambda D is equal to AX. So if you increase the D distance, then the X distance will increase. I call this the torchlight effect. You remember in some of the classes I show you how when you pull the torchlight far away from the wall, the image is getting bigger and bigger. Light source of different colors is used. Okay, let's recall this. All right. P, I, B, G, yo. Purple, indigo, blue, green, yellow, orange, and red. As we move from purple to red, the wavelength is increasing. The wavelength is increasing. So when you use the wavelength of red, which is longer than the wavelength of green, for example, all right? So for sure, when the wavelength increases, the distance of X will increase. So will increase, all right? So when you increase the wavelength of the light, so you change the light source from a shorter wavelength to a longer wavelength. So as the wavelength increases, the distance of X2 will increase, because that's how the formula shows. Wavelength increases, distance of X also increases. Next, one of the double slit is closed. See, if we close one of the, there were two double slits there, right? You go and close one of it. So there's no effect of interference. No effect of interference. You won't get it. You won't get it, right? So these are the factors and effects you have to know. Another thing here, you have to know the idea of coherent. Coherent shows that the two light sources are identical. They have the same speed, same wavelength, same frequency, and they are in phase. Both of the wave will experience crest and trough at the same time. So it's called in phase. The next one, sketch. I'm still at chapter wave alone, so chapter will take a lot of time. So, okay. Sketch a graph to show the relationship between the wavelength and frequency of wave with constant velocity. So, look at the formula again, right? The formula says that speed is equals to frequency times lambda. So, lambda equals to speed over frequency. Bawa turun lah. So, sketch a graph to show the relationship between the wavelength and the frequency. So, your graph should look like this lah. All right. Wavelength and frequency. So, it should be inversely proportional. Inversely proportional. Inversely proportional. Okay, done. Next, we continue. So make sure you know this idea. Methods to reduce echo. Echo is the idea of reflection of sound wave. So if it's a closed environment, use curtain, soft material, soft board on the wall, or carpet on the floor. All this is to prevent, because they will absorb, these materials will absorb the sound wave. We are reducing the echo effect. All right. Then the behavior of water is moving from the open sea towards the shore, the bay area. The water near cape is turbulent, while the water near bay is calm. We did this earlier, if you remember. So in the open sea, the wavefronts of water waves are straight and have uniform amplitude. Water waves undergo refraction as they approach or get near to the shallow water near the beach. The velocity decreases because of refraction. The wavelength also decreases. The water becomes less energetic, become very calm. They are spreading their energy to a wider area. So wavefront's amplitude increases at the cape, but not at the bay area. Bay area is still low, right? The spreading of wavefronts causes the amplitude to decrease at the bay, and the water becomes calm. Very common question, so go through this properly. Another question of interference, this time sound. Again, the figure below shows an arrangement that is used to study sound interference. I think most of you have did this question with me in the class earlier. Okay, in this experiment, two speakers A and B are connected to an audio signal generator. Each of the speakers produces a sound with a frequency 1500 Hertz. A student that is walking along a straight line here, YZ, hears a loud sound that becomes softer alternately. Points P, R, and T are the positions where the sound is loud. P, R, and T sound is loud. That means P, R, and T are constructive interference point. Q and S soft, so destructive interference point. Name the phenomenon that produced the changes in the sound strength. Interference of sound wave. This experiment must be carried out in an open area, yes, to reduce the effect of echo. This effect of echo. The velocity of sound in air is 320 meters per second. What is the wavelength of the sound that is produced? So let's calculate the wavelength. So speed equals to frequency times lambda. The speed of the wave given 320, frequency given 1500. So what is the wavelength, guys? What's the answer? Boys?
0.2133.
Yeah, 0.213. Thank you.
Sure, what's A?
A, interference. Okay, next. The distance between speaker A and B is 1 meter, and the distance between the speaker and the straight line YZ is 3 meter. What is the distance between P and R? P and R should be a perfect X. Okay, just now I told you P, R, all are constructive interference. So we're looking for distance of X. Okay, again. Lambda is equals to AX per D. So X should be lambda D over A. Lambda was 0.213 meter just now. Correct, right, guys? Correct, right?
Yes, yes.
Yes.
X is a distance of 3 meter. And A is at a distance of 1 meter apart. So what's the answer for X, guys? No.
So wait, counting.
0.639.
0.639 meter. Okay, done. This is the answer for D. This is the answer for D. Okay, done. Okay, now, if the frequency of the sound that is produced is higher, what will be observed by the student? Explain. You see, guys, speed is equals to frequency times lambda. Frequency is equal to speed over lambda. So when the frequency is higher, increases, the lambda decreases. When the lambda decreases, lambda is equals to AX over D. So when the value of lambda decreases, you should know that the value of X also will decrease. So what will be observed by the student? The distance between two consecutive loud sound decreases. The distance between two consecutive loud sound decreases. That's what the student will get. Any question, anyone?
Sir, can repeat what you said?
See, as the frequency of the sound produced is higher, so look at here. When you have the formula of speed equals to frequency times lambda. So when the frequency increases, the lambda is decreasing. The lambda value decreases. So when you increase the frequency, lambda becomes shorter. So when the lambda decreases, X distance also decreases. So the question says, what will be observed? The distance between two consecutive loud sound position decreases. Got it? Boy?
Yeah.
All right, done. Another question. I think this is the last question. Yeah, another question. Figure shows the use of sonar equipment, sound navigation and ranging equipment to measure the depth of the sea. State the phenomenon of sound wave applied in sonar equipment. What is the phenomenon? Reflection of sound wave. Reflection of sound wave. Sound wave with the frequency given are used to determine the depth of the sea. Speed of sound wave is given. What is the wavelength of the sound wave in the sea? Wavelength. So A answer is reflection. So as we know, speed is equal to frequency times lambda. So lambda should be speed over frequency. The speed given 1500 meter per second. The frequency is 6 times 10 to the power of 5 hertz. So what should be the lambda, guys? What is the wavelength? Girls, boys, anyone?
2.5 times 10 power negative 3.
Yep, thank you. 2.5 times 10 to the power of negative 3 meter. Okay, thank you, Mr. Sean. And next one. If the time interval between the instant the sound wave is sent to the instant the echo is received is 1.5 second, what is the depth of the sea? So speed supposed to be distance per time. So distance, which will be depth in this question, should be speed times time. But as I said earlier, to the instant echo is received, send to receive. So you have to divide the time by 2. The speed is 1500 meter per second. The time given is 1.5. Please divide it by 2. So the depth should be proper.
1125.
Yep, 1125 meter. 1125 meter. Done, guys. Done, done, done. Okay. Any question, anyone? Eugene, okay?
Yo, wait. Too fast already.
Oh, okay. Copy first. For chapter wave, so I think make sure you go through all the formulas, limited formulas here. So make sure you know all the calculations, especially refraction, interference, and the depth. Okay, make sure you know certain definitions, which might be very important. All right. I'm targeting interference. So go through all the sort of interference of light, sound, water, everything, and electromagnetic wave. Make sure you know about them, or what the usage, how they are broadcast. Okay, the spectrum of them must know. Their spectrum must know. Basic calculations and how to identify. Single slit, double slit must know. The lambda equals to ax per d formula of manipulation of that formula you must know. All right. All the other parts like reflection, water wave behavior from a deeper to shallow area or the bay area, then sound wave, echo, reflection, interference, all better concept, all this. I think these are the most important parts in this chapter. But this chapter will be very, very important this year, if I'm correct. If I'm correct. If I'm wrong, no, then I'm wrong. This chapter might be very, very important this year if you see this. Okay, see here. For paper 3, question 4. Paper 3, question 4. You look at it here. I went back as far as 2009. Chapter 3, electromagnetism. 2010, electromagnetism. Then was wave. Then electricity, 2012. Then again wave, 2013. Then 14 was electromagnetism. 15 was electricity. Back to electromagnetism in 16. 17 back to electricity, then 18 was electromagnetism. Last year 2019 was electricity. So if you look at it here, since 2013 until now, they have never tested question 4 paper 3 on wave. Sudah lama tak keluar. So I will encourage all of you to go through all the chosen experiments from this chapter. For question 4, paper 3. Try to go through. Now you got time, please go through now. Right now you have the time, please go through. So it's in your notes, you can check there later. Right. We are here. Okay, done with